Hey folks.
Hello everyone. Yeah, Pratik, you seems to be a bit tense today.
Yeah, actually, I had one issue with my ML model application. So basically, what it was like, I was building a model on NLP. The thing was, I was gathering the text data and stuff from one side, like data ingestion. I was doing that stuff on a separate base, and I was building my model on a separate base. So the problem was, my application was totally different. So it was like three different parts of my life cycle. So I had to figure it out, like how to integrate it and streamline the process. So I could not figure it out, like if there was one process where we could take care of monitoring all steps of that ML life cycle.
Okay. So, do you know about ML ops?
Not quite, but yeah, I have heard of it.
The various problem which used to occur when you deploy the model. If when you used to deploy the model, you are going to connect it with your business application to abstract the useful information or predictive value of whatever the use of model is. You are going to extract it in your application which is built for businesses like that. But there are many problems used to occur in that. Okay, whether it's lack of iterative deployment, or we can say a long chain of approvals, or we need to do the monitoring manually. Okay, and there are like a lot of stuff when the data trend changes, the variety of the data you give, the accuracy increases, and there are like lot many stuffs. So this needs to be solved. So for that reason, MLOps comes into the picture. Okay, it helps in a various ways,
Oh,
like
that's
whether it's, yeah, it helps in a various ways, like whether it's reducing the IT operation cost or speeding up the solving and deployment stuff, and also automatically monitoring things. Okay, it helps to have an increased reliability, and also at the same time you will be having like automatic anomaly detection, so you would not have to worry about it. Also providing a better infrastructure, and there are like lot many stuffs to discuss on. So today we will be
yeah.
having a session on
uh,
operationalizing ML model on cloud. So so today's speaker is Gopala Dhar. So he is a Google AI engineer. So welcome, Gopala sir.
Hey folks, I am Gopala. So I work as an AI engineer in Google Cloud. Yeah, so most of my job revolves around building ML models, maintaining ML systems, and creating scalable workflows for operationalizing machine learning solutions specific to certain industries. So yeah, I mean, just as I sort of do it in my day-to-day routine, I wanted to make sure that anyone who's operationalizing machine learning models knows how to do it. It's really not that difficult. It's a very straightforward process, and we're going to discuss that end to end today. Um, the only few things which I would like to you to know before we begin this session is that there are a few ground rules on how I generally operate. Um, Please call me by my first name. That's the first thing. Second thing is that let's keep this session informal. If you have any questions, feel free to put it in the chat. Or if Pratik Rishikesh, you have any questions, feel free to interject and ask them. There's no stupid questions. There's no simple questions out there. Uh, right, and most importantly, feel free to enjoy the session, and if you feel like I'm boring you, let me know. I will change my trajectory and put my course of action. Anything which I say in this session is basically just based off my own personal opinions, and it doesn't reflect my employer whatsoever. And yeah, that's pretty much about me. So let's get started if you're good with it.
Yeah.
Cool. All right. So, yeah, I am going to be taking the session on operationalization of ML models, or how do you operationalize ML models. Generally, when people speak about operationalization of models, it's generally very obfuscated. So I'm here to sort of clear out all the steam. By the end of this session, this is what you should expect. You should expect to have an overall high-level understanding of what operationalization of ML is. What are the different steps in an ML lifecycle? and how do we sort of you know build an ML model from scratch and then move it to production. Each and everything which lies in between, I'll try to cover that. This is going to be a high level session. That means I would not be touching on any sort of code or any low level design. It will be a high level approach, high level presentation to give you a better idea of what happens in the industry. um, yeah, so let's get started to the next slide. All right. So, first question which you should be asking if you're if you're newcomer to cloud and machine learning in general is that why should I even care about cloud for machine learning workloads, right? You have a machine learning model. If it's a simple, straightforward model, you can build it on your system itself. You have a laptop, you can build it on that. You have a desktop PC, you can build it on that. But according to VentureBeat.com, more than 87% of data science projects, machine learning projects, never make it to production. And as a person who's worked in this field for quite some time, I've observed that a lot of people are really, really good at building machine learning models. They're super talented, and they know their way around things. But when it comes to productionizing models, putting and making those models which you and I interact with, they suffer a lot, and eventually the pipeline just fails. It just fails to deliver, right? So always remember that anything which you build, no matter how awesome it is, if it cannot deliver some value, it's not gonna be useful, right? At the end of the day, the value is what matters, right? So it can be a technical value, a business value, a people value, any sort of value, right? So let's discuss this, right? Why do most data science projects sort of just fail, right? Why do they fail? Modeling isn't difficult, right? We've come a long way in machine learning and deep learning. Why does it still fail? The first issue which comes is because machine learning is a different thing altogether as compared to your regular application development. It has a whole lot of different shortcomings, you can say, or it has a whole lot of restrictions. It comes with its own set of restrictions. The most prominent one being is that you do not have enough compute generally if you want to scale up your system, or if you want people to work with your models and interact with them. Users interact with your model. You want to deploy to a machine which has enough compute for it, and generally that's not going to be your own machine. And when you have some sort of a pipeline going on for it, then it becomes a different task of how do you operationalize the pipeline, how do you make sure that the pipeline doesn't fail, right? How does it sort of work even when there are millions of hits to the model in 1 second, right? So that's what we're going to talk about. So we can go ahead and move to the next slide now, right? Cool. So this slide is just going to answer your question about what is ML modeling. So this is probably one of my most favorite diagrammatic representations of machine learning systems in general. You can see the dark gray block which says ML code. That's where your ML code sits. In the grand scheme of things, which is configuration, automation, and all those things that you can see in this diagram, ML code is a very teeny tiny bit, and that is the reality of this world that we live in. Machine learning code, oftentimes, which you will also observe, is often not that it's the most difficult thing, but it is the thing which is sort of the least impactful in the grand scheme of things, right? Your ML code will just sit there, but on its own, it's almost useless, right? You need a serving infrastructure. You need a process management software. You need to do model analysis. You need to be able to monitor your models which you've deployed. Those are the things which we talk about when we have a model which is deployed. But what about pre-deployment steps? You need data verification. You need stuff for feature engineering, data collection, testing, configuration, and even automation, right? So this is like the holy grail. This image will sort of give you a good idea that no matter how good your model is, TensorFlow, PyTorch, the latest buzz out there, it's just going to be residing. It's just going to be sitting in that small box of ML code. That's where all of your ML model is going to live. So essentially, whatever things which are outside of that small gray blobs is what ML ops or ML operationalizing generally consists of. Right now, this might seem like very I mean, these might seem like a very high level things, like abstract, which doesn't make any sense. Like, what do you mean resource management? What do you mean process management? Monitoring. These are all very abstract things. But as we go around in this presentation, we will have more and more, information and understanding about what entails in an ML modeling or an ML processing. So let's firstly deep dive into the small gray box, that is the ML code, because obviously that, as you can see, it's the centerpiece, or you can say it's the it's the brain of the system, and rest of everything else is the different body parts of this ML system, right? Next slide. Cool. So let's talk about ML modeling, and in ML modeling, let's discuss what are the different types of models that you might want to build, right? So in general, when we think of ML modeling, we may think of writing the code ourselves and building complex deep learning systems, building neural nets which are huge, building like thousands of parameters long neural nets, which is fine, right? People do that all the time. However, whenever you approach a problem, there's a certain specific way which you should follow, your modeling approach. The first and the foremost thing which you should think of is that, do you have data, right? And this is like the real world sort of punch in the face for machine learning. Do you have data? If you don't have data, you most likely won't be able to do machine learning from your own sort of data, because you don't have any data. So the next thing which you should look for is that if you don't have data, what should you do, right? If you don't have any data, you should go for a no-code approach, which is systematic APIs. And I'll talk about that a little more in a while. But let's say you do have data. You have a little bit of data. Let's say you just have 20 or 30 samples of each of your each of your tasks. Let's say it's an image classification task. Simple example could be a dog versus cat classifier, right? Let's say you have a certain amount of data for it, but it's not enough, right? So what should you do at that time? Well, at that time, you can use a low code solution. So a low code solution like AutoML is something which is often used. It's generally really good for creating baseline models, because it doesn't have that much requirement of data. That is especially true because AutoML has, it uses its own set of transfer learning based algorithms, which are a little which are a little complex in nature, and those sort of help you build good models, good baseline models with minimal data. And the third approach, which I think most people are familiar with, is the custom modeling approach, wherein you are the whole you own the whole tech stack. You write the code in each line and each variable. You can use a bunch of frameworks like scikit-learn, TensorFlow, and if you're doing research, you may even use JAX. Right? So, as you can see, there is no right way of solving an ML problem, or there is no wrong way of solving an ML problem. It all depends on what do you have. So this list is ordered in the increasing level of complexity, or the increasing level of hands-on work in code, and especially in data. In machine learning, it's always about data. So, for example, I'll take this cats versus dogs classifier example. If I have no data, I can go ahead with a Vision API, which is provided by Google. I can just run it through these images and get enough information to sort of understand if it's a cat or a dog, right? If I have a few data points, I can go ahead and use AutoML Vision and use that AutoML sort of algorithm to figure out if I have enough, if I can build a classifier just with 5 or 10 images of cats and dogs, using transfer learning that internally abstracts away and build a model. And lastly, if I have a lot of data, I have thousands of images, and I want to build a really sophisticated model, deep learning model, I'll go ahead and use TensorFlow. But again, like I said, there is no wrong way or right way of building. It all depends on your use case, right? So I'm just gonna give 1 second so that you can absorb this slide. Cool. So this was the first step, right? In the small box which we just saw, this was the first step of selecting the model, or which model should you select. Right? People often ask which model to select. The right answer is that there is no one right answer. Depending on your data, you can select either of these three, and all of these three, you'll be surprised to know, are used quite often in the industry. Yeah, and I think we can move to the next slide now. Cool. So you selected a model, right? Out of those three models, you just selected a model and you built one, right? In case if you're selecting an API, well, then it's not technically a model; it's a pre-built model which uses state-of-the-art internal models which Google has built through their research teams and engineering teams. You're using that model. But what if you build a custom model or you build a AutoML based model? Like those are still models which you build and you sort of own, correct? So then what is the need of artifact tracking? And first of all, what is even artifact tracking, right? I mean, what does an artifact even mean in this context? So essentially, what I mean by artifact tracking is basically just a way of saying that, hey, I have this model, but I want to see what all data was used with it, or what all parameters this model uses, or when was this model trained, and what was this metrics, and all those things, right? So all these things which sort of define a model, which sort of are the characteristic of a model, such as the data, the metrics, and all these things, like I just mentioned, these sort of form an artifact. So that's why artifact tracking is important. So let's go each and every point one by one. So the first reason why it's important is because it helps in tracking the model and the data lineage. And also your experiments. So if you have a model and let's say you train 10 versions of this model by changing the data, changing the parameters, each time you change something, you need to be able to track it, and you need to be able to go back and understand, okay, I changed this feature or I changed this parameter, so the model improved by 10 percentage points, something like that. The next thing is data lineage, right? Oftentimes, people, when we talk about machine learning systems, we talk about data because ML systems are inherently dependent on data. It's the GIGO principle, garbage in, garbage out. Yeah. So, in this, when we talk about data lineage, what I mean is that if your data is changing, you should also be able to track that. You should be able to track the trends in the data so that you can confidently explain and explore what is going on and why is it behaving the way it's behaving. And the last thing is experiments. So machine learning is all about running experiments, right? It's all about finding the right model, the right hyperparameters, and all those things. So whenever you run experiments, it should not be open-ended. It should not be like blind experiments wherein you're not tracking anything, right? That is not a very scientific way of running experiments. So you need to have a platform, you need to have a space where you can do all these things and sort of get all this information logged, right? That's where I segue into the second point, which is evaluation of your models and experiment run. So your models you've trained, let's say you've trained 10 versions using the same data set, but you've changed parameters here and there. You've changed the model depth, you've changed the hyperparameters and all that. So you want to see how your model performed each time, right? So that you and your data science team can take an informed decision. And generally, whenever you are pushing a model to production, you are pushing a model out in the open, you would want to have a very strong story depicting why it should be pushed to prediction. So this kind of evaluation exploration will help you and as well as your stakeholders, as well as your teammates, to understand, okay, why is model A better than model B. And of course, it helps in storing the model metadata, which, like I just discussed, it's all the information which defines a model, right? So how do you do it? Right? All of this is good talk, but how do we actually do it? Well, if you use Vertex AI, if you use Google products, inside GCP, you have Vertex AI metadata and experiments. So essentially, what these two things do is that they make sure that you're able to track your model lineage. You're able to track different model experiments that you run and also see how your model is performing. So if your model is improving, you can see that. If your model is degrading, you can see that. So essentially, it's a way for you and your team to make sure that all the models that you're training are being trained in a successive fashion, right? And it becomes especially useful when you have bigger teams which are experimenting with a lot of models, right? You need a one-stop shop where you can see everything what's going on, right? All the things from A to Z should be in the same place. Because modeling and monitoring one model is easy, but when you have 100 concurrent models, then it becomes a little complicated. That's why you need artifact tracking. Next slide, please. Cool. So, well, you built your model and you've sort of understood the requirement of artifact tracking. You've set up your artifact tracking. You have your artifact registry, model experiments, and now you figured out the best model, right? So, what you want to do now is that you want to deploy a model. So, deploying a model in itself is a little tricky. It's a little complex. But first, let's understand why is that so. The thing is that for a conventional IT application, the system's nature is deterministic. So what I mean by that is any IT application that you build, you basically know all the failure points. You know how it's going to perform, and you know if you give an input of A, the output will be B or C or Z. You can test it out. I mean, we have unit testing, integration testing, and all those sort of testing. Different testing paradigms are there for an IT application to make sure that it doesn't fail, and we have covered all the edge cases. That is what I mean by deterministic. But in the case of an AI application, the system's nature is stochastic. So by stochastic, I mean that it's probabilistic. We may or may not always have an answer to a problem, and it may or may not behave the way we want it to behave, right? um, just as an example, right, if you build a model, you will not be 100% sure. Let's say it's the classification model, cats versus dogs. You cannot be 100% sure that whether or not your model will always result in the in, let's say, a cat being classified as a cat and a dog being classified as a dog, right? You cannot be 100% sure because it's a probabilistic model, right? Machine learning models are never 100% accurate. So that is the first sort of a challenge which comes. Why is it a challenge? We'll come to know in a little while. We can go to the next slide. Cool. So deploying the model, we saw it's stochastic, but what does it mean? Like, what does deployment even mean? So if a layman is wanted to understand what deployment means, it just means that you want to host the model on a machine so that the end user can interact with it. So let's say I build a model, I build a classifier which can let's say predict whether or not it's going to rain tomorrow. 1 or 0. 1 means it's going to rain, 0 means it's not going to rain, and I want you or I want anyone else to interact with it and sort of predict it for their their geographical location, right? Given their let's say given their latitude longitude position, they want to figure out if it's going to rain tomorrow or not. I've built the model, but I want you to try it out. I want you to sort of experiment with it. I'll have to deploy the model. I have to upload my model file somewhere where you can interact with it and you can use it. So if that's it, right, all I really need is a machine, right? Like I said, the machine can be a local machine. I can deploy the model on my own machine as well. So if I have my, let's say, my laptop, I can deploy a model here, and using local area network, a LAN connection, anyone who's in my local area will be able to ping that server and get an output. We can also use a virtual machine. Like I can have a Linux instance running on my on Oracle box or some other software, and sort of use a virtual machine to deploy my model there. Or I can use the same virtual machine on cloud, right? I can use, let's say, GCP or AWS or any other cloud and use their virtual machine for deployment. So this is fairly straightforward. I mean, you just have to deploy a model, you have to build a wrapper around it and go for it, right? So when we talk about deploying, we want to talk about serializing the model. That's where you use like you can use things like Docker, where you can sort of put all of your model files together in a container. It's called a container, and build a system where you can just push the Docker file, run the Docker file, and just start getting predictions, right? Or you can also use protocol buffers, which is protobuf. It's a way of serializing your data and using that. In this context, you can use it for your model prediction, hosting the model. You can use gRPC based hosting requirements. Instead of REST API, you can use gRPC, which is often much faster but a little more complex to implement. So it's straightforward, right? You need a machine. You can just deploy it over here and you're done, right? Your modeling is completed. But is that really the case? Let's find out in the next slide. Cool. So ML model deployment is a little tricky. It's not that straightforward. We'll just sort of go ahead and look into each and every point of that. So the very first point is that ML models are data dependent, like I just mentioned a while back. ML models, you should always remember, is follows the principle of GIGO, which is GIGO, garbage in, garbage out. If your data is a heap of garbage, your model is gonna learn garbage and give garbage as an output. So for ML models which you want to deploy, you want to make sure that the data is proper. It's not just some random things which it's learning, and it's just some random information it's just picked up, or it's just learning noise, because that's not going to help your system, right? Second thing is that modeling needs a reliable compute. For a number of reasons, this is a very, very extremely important point. The first reason, what I would think of, is that ML models generally, especially if they're deep learning based models, they are often they're often intensive in compute. They use like these huge neural networks with a lot of weights. So they need to have that much amount of compute with them so that they can quickly and reliably give you the output, right? Also, they need memory as well, because if you want to use this serialized model, you need to deserialize it in memory and store it in memory so that you get really quick output. And Yeah, and they have intricate dependencies. Basically what it means is that ML models, especially if you're running it on GPUs, graphic processing units, you may run into a lot of dependency constructs, because GPUs use a different architecture, right? GPUs are more parallelized, and they use, if it's an NVIDIA GPU, it will use a CUDA based architecture. So you need to have those CUDA driver and CUDA dependencies in place. So generally it's not as simple as just installing certain packages and spinning up a server and just pushing your JavaScript files and having a website up and running. It's much more complex than that. Your dependencies often will make or break your system, especially if it's an intricate ML model, right? Even if you have things which are computationally expensive, which run on your GPU, or which have like a bridge between your GPU and your CPU, they will require a lot of dependencies which are generally a little complex to sort of navigate around. So that's why we generally prefer, in the industry, we prefer using Docker. And the last thing is the post deployment validation. So unlike a conventional application, like conventional IT application where you have unit testing and integration testing, you can still have unit and integration testing for ML models, but your actual model performance will depend on your validation, right? Especially on how it performs post deployment. So after I've deployed my model, is it reliably giving me the results, or is it just spewing out some garbage values, right? So if it's a model which is gonna let's say predict if tomorrow is gonna rain or not in a certain area, is it actually doing a good job predicting that? How's the accuracy, or how's the recall, how's the precision? All those kind of things, right? All those kind of statistical measures need to be defined, and it becomes a little complex because you need to do that kind of validation checks after the model is in production, because that's where the real data comes in, right? After the model is deployed, somebody will use it, my end users will use it, and I'll get some data. So this is why ML model deployment is a little tricky. It has a little bit of caveats here and there. So yeah, we can move to the next slide. Cool. So now that you've understood that ML model deployment, you need to make sure take care of a few stuff here and there. The logical question is that where should I deploy, right? I mean, like I said, you can deploy it on a VM. You can even deploy it on your local system. You can even deploy it on a cloud VM, right? But which one is the best one for you? And oftentimes there's no right answer or there's no wrong answer. It depends on your application. So here's a little sort of a chart, or a little like a list which is prepared to help you make the informed decision. Um, so the very first thing which I mentioned over here is the Vertex AI endpoints, right? So this is a fully managed compute which is offered by GCP, which we often use. So when I say fully managed compute, it means that I can just provide the model details, like all the model files, the pickle files, the TF record files for pre-processing or whatever, and even the job lib files. All those information I can provide, and that's it. I This everything else, spinning up the instances, taking care of my infrastructure, is taken care by the endpoints. And the good point is that it can also auto scale, which means is that if I specify I want to auto scale up to 10 instances, it will do that automatically based on the load, right? Based on the traffic. So that is a fully managed compute. It's called Vertex AI endpoints. But sometimes you want a little more customization, right? You want a little more flexibility. You want to be able to do a little more, right? And maybe you have some dependencies which are not limited to just Python, which are system dependencies, right? Which are some OS based dependencies which you need to install before you can even deploy a model, right? That also happens. So in that case, you can go for a serverless container deployment, which is through Cloud Run. So if you have a an intricate model which cannot be somehow deployed to a Vertex AI endpoint, what you can do is that you can build a Docker container, put all your model files in there, have all your installations, and then deploy a model, right? Because, like I said, every each and every one of these suggestions over here on your screen is not absolute. It has its own advantages as well as disadvantages. So Cloud Run, definitely it's a good product. You can use it to use a serverless container deployment. It's easy, extremely easy to use, and you can also have multiple instances, and it also supports auto scaling. So that is also a good thing. The key to remember is that it's serverless, so that means you still don't have to worry about setting up the infrastructure, or worry about cost and all those things. Fully managed and serverless items are often always pay per use. So as and when your as and when your traffic to your endpoint or to your model increases, the cost will increase, otherwise it won't increase, right? So, what if you have a little more complex models which needs a lot of backend calls, and this model is in its own it's utilizing three four other models, which happens, right? Oftentimes we also build machine learning models which are not a single model but like an ensemble of multiple models. So at that time, sometimes it doesn't make sense to use Vertex AI endpoint or Cloud Run, right? Because of some compute considerations or some memory considerations as well. So instead, what we can do is that we can deploy our model, again containerized, to a managed Kubernetes cluster. So a GKE is the Kubernetes cluster where you can sort of have one or multiple models deployed, and those models can interact with one another. There is a little learning curve to it, and it's not that straightforward to use it. However, it is a very powerful tool, and most companies as well as most professional organizations across the globe deploy and manage their models using this kind of compute technology, like this clusters based approach, right? Like it can be Kubernetes or some other clusters as well, because it's generally extremely reliable and it's highly scalable. Again, it auto scales, and it's generally quite powerful, to be honest. And the last option is a cloud VM. It's a simple compute engine, which basically means that you are spinning up an instance, like I mentioned like 2 slides back. You're spinning up an instance in someone else's computer, which is basically a compute engine, and you're just deploying your model there. You're setting up a server there, or you're using Flask or some other thing, and you're sort of hitting the model's endpoint to that place. So if you observe, this list is also in the increasing order of complexity. However, the complexity which I'm talking about here is the infrastructure complexity, or in other words, how much do you have to manage? Right? And when I say manage, I mean the infrastructure, because for each of these things, each of these approaches, there is an underlying infrastructure, which is a compute machine, and all those other, it's spinning up instances and using memory. So somebody has got to manage that, right? Uh, for fully managed and serverless things, you don't have to worry about your compute or setting up the compute, setting up your VPCs, firewalls, and all those subnets and all those things. You don't need to worry about that. Most of the things is abstracted. However, for these cloud VMs and Kubernetes clusters, if you want an end user to interact with these, you have to set up firewall rules, you have to set up reverse proxies, you have to set up a whole lot of other things as well, which generally takes a little more domain expertise to perform. So depending on your use case, you can choose any one of these approaches. Cool. So now we can move to the next slide. Yeah, we can move to the next slide. All right. Now, after your model is deployed, right, you want to be able to infer from that model. So what do I mean by a model inference? it really means that you are just hitting that endpoint and getting some output, right? You're getting some prediction. That's what we mean by inference. Now, in general, when we talk about inferencing, there is two types of inferencing. There is batch and there is online. So let's talk about the batch inference first, right? What do you mean by a batch inference? So essentially, if you have a model which is trained, and let's say it's sitting on your computer or on some VM, and you have a bunch of data which you want to get the result for. So you want to run the model against a set of data which you already have, right? It's a batch of a data. That's why it's called a batch inference. So think of it like you want to you have a 1 GB of a file or 1 GB of a bunch of files, and you just want to run it through the model and get the output, and then you will sort of analyze the model. That's what we call in industry as a batch inference. All right. So batch inferences. Let's look into the pros. What are the pros of batch inference? So the first pro is that it can be done on large corpus of data. So essentially, doesn't matter how large your data is. If your memory or your machine can support it, you can do it in one go, or you can create smaller batches. So if let's say my memory in my machine is just 2 GB, and I have a data worth, let's say, 10 GB, well, I can just divide it into chunks of 2 GB and run this inferencing. So I can just do this kind of model inferencing on a huge data set without any issues and concerns. The next thing is that model deployment is optional. So essentially, if you're doing a batch inference job, you don't have any necessary need to serialize your model, that is, save your model and then upload your model in the same instance or in the same Python core or in the same notebook where you've sort of trained your model. You can load the model and run predictions on it, right? So you don't need to deploy a model. You don't need to worry about all that. You can still do it if you deploy a model, but then you will have overheads of network and bandwidth and all those things. You can avoid all that by directly using a batch inferencing. And it's relatively cost effective because there is no constraint of network, or there is no IO concerns. It's generally really cost effective, and that's why batch inferencing is generally used when you have a large corpus of data and you want to analyze it at your own means. So you'll have a bunch of data, you will use it through you run it through the model, get the output, and save the output in some table, or save the output in some file, right? And then you can, in your own time, you can sort of analyze what's going on. This is generally what's done in most sort of experimental approaches. So what are the cons? uh, the cons is that the latency is often quite high because the way this batch inferencing is made to work, there is no consideration for speeding up the process of inferencing and anything. It is more or less more focused on getting the job done rather than getting the job done fast. Essentially, your model is just based in memory, and depending on your data size, it will take a lot of time, right? It can even take hours to run. And another thing which is quite interesting is that it's often ineffective for unknown distributions. So let's say you have a long tail data distribution, right, which has a very often the data is changing at the very end. So when you use that sort of a data set, which has like a long tail distribution, which is a little unknown, and you use it for batch inferencing, it's often going to yield results which are not very convincing because that model itself is sort of static in nature. It's not changing, and that's why it's often ineffective for this unknown long tail distribution if you do a long tail distribution plot. So that's about batch inferencing, but where do you use this batch inference, right? So the very good example was when I read about I think Swiggy and Zomato and a few more of these applications. They use batch inferencing to run recommendations to generate your home screen. So anytime you open these apps, you might see recommended restaurants, recommended cuisines. The way it works is that once every day, or I think once every week, I'm not sure, they run recommendations, generate some output at their own time, and save the output in a database, and then query that database whenever you open your sort of application. At that time, the database is queried to give you the model out. So the model is not being called when you open the app. Rather, your output is already saved in some database, and that's being called. It can be a database. It can also be locally saved in your phone also, so depending on the application. Same goes on with Netflix, same is with Amazon Prime. Things like even even applications like Hulu and all these things, they all use the same sort of an approach, right? So that is about batch inferencing. So now we can move to the next part, which is the online inference in the next slide. Cool. So essentially, wherever batch inference lacks, online inference rocks. So online inference is really great for real-time inference, right? If you have like one data point which you want to get an output for, you would go with an online inference. So if there are 20 people hitting the model at the same time, it's going to work out pretty well. And the other thing which it's great for is that it's great for unknown distributions, right? So what do I mean by that? What do I mean by saying it's great for unknown distribution? What it means is that if I have a long tail distribution, like I just discussed a while back, since the model is sort of it doesn't know what sort of distribution it's going to get, and it's invariant of all the other data points, it will work much better than a batch inference sort of a paradigm. So again, these two might seem like small points, but online inference is often used much more vividly, and let me put it this way: there's much more used often in the industry as well. So anytime you're doing any sort of shopping or ad based recommendations, it's often online, right? So what are the cons, right? So it's often much more compute and memory expensive because let's say you are running a virtual machine or an endpoint like we discussed a while back. So you have like a one compute machine, and let's say I have 100 users. So 100 users are trying to attempt to run the model at the same time, right? So it is going to be taking up a lot more compute, right? Because it's like instead of one big process, it's 100 small processes. And if you know, in general, if you are aware about how CPUs work, CPUs are generally exceptionally good at processing big things than processing multiple small things. So that's where it becomes very, very expensive, right? And if you want to serve, let's say, a million people or a billion people, right, you need a lot of compute, right? You need a lot of hundreds and thousands of machines spread across the whole world to hit those requests. So then it becomes a little, it becomes a little expensive. Next thing is the inference compute needs scalability. Like I mentioned, if I deploy a model and tomorrow it's just being used by 20 people, that's a different story. However, if it becomes like super hit and people want my application, my weather prediction application, then it's being used by, let's say, 10,000 people or 1 lakh people. So at that time, you need to be able to scale this system. So that's where the model compute comes into picture. Otherwise, your model is going to fail. Like you're going to hit your endpoint and it's just going to go away, right? It's not going to work. It's going to throw errors. The next thing is that the monitoring systems are complex. For any batch inference jobs, you run the prediction, you save the output in a database, right? You can query that database and essentially you can get all the information out, and you can run statistical tests, covariance tests, chi-square tests, whatever you want to run, and you could know how your model is performing when you run a batch inference. But what do you do for an online inference, right? An online inference basically means that if somebody is hitting the model, it's just giving the output to them, and you can't predict what's going to be your traffic, right? It's a spiky traffic. So monitoring systems are complex, right? How do you monitor this? Do you monitor each request, or do you monitor alternating requests? How do you scale up if there are a lot of parallel requests going on? So that's why I say it becomes complex, and it generally often, of course, it'll cost a lot more than batch inference because like I said, you need to take care of scalability, take care of compute, take care of networking charges, storing CDNs, a lot of different things, right? So hosting models online is often good if you want to showcase your work, but scaling them out becomes a challenge. So remember the first slide, that ML systems often fail. This is also one of the reasons, right? You need ML systems which are robust and which don't sort of crumple under their own weight. So where would you use an online inference? Well, they are used in a lot of different places. Online inferences are used when you're sort of running a program, or let's say you're opening up an application and getting targeted advertisements, right? Targeted advertisements are helping you to find the right fit. That is an online inference. It takes your data and sort of runs it through and gets you some output. Or when you're using TikTok, or you're using something like a YouTube Shorts. So your immediate interactions are going to determine how it's going to be, how it's going to perform in the next phase or set of things. That's where your online inference comes to play. So online inference is often also used a lot. It's just that it's a lot more expensive and a little more complex to monitor. Okay, so now move the next slide. So cool. So you deployed your model and you're able to do inferencing, but you still don't know if your model is performing well, right? Because like I mentioned a while back, if you have an online model, model which is deployed in an online fashion, it's a little tedious to know what's going on, right? You will not 100% be confirmed that the model is performing well. And due to the nature of data science projects, you cannot be on the vision will of the model, right? You need to be able to quantify your metrics. That's where Canary deployment comes into picture. So Canary deployment, also known as a gradual release, is a way of only allowing a certain traffic to hit your model, while the rest of the traffic can hit to the baseline model. So it's very, very useful. So let's take the same example of this this weather application which I've built, right? So let's say tomorrow I get my hands on a little better model and I build that model, right? Let's say I was initially using a regression based approach, a logistical regression based approach, but now I have a deep learning model, right? So while I train this model, I think that it's going to be super awesome and I build this, but I'm not sure how it's going to perform in the real world data set, right? In the production environment, how it's going to perform, I don't know, right? I cannot have an answer to that. So what I will do is that I will expose my audience, I will expose my end users to this model, and I will see how accurate is the results, right? How accurate are the results? So how do I do that? So the way we do it is using the Canary deployment. And what are the sort of benefits of this is essentially just it will ensure that you are reducing the risk of exposing a new ML model. So what do I mean by that is, let's say if the model which I've built is really good, but unfortunately it's overfitting and I don't know it, right? Or the data science team doesn't know it's overfitting. So such a model, if you directly deploy into production, it's going to fail. It's going to fail and it's going to cause you millions of dollars of loss, right? You don't want that. So you need to reduce the risk. You cannot eliminate it, but you can reduce it. So the way you do it is that you control the traffic that is hitting your model, right? And by this way you can run real life model validation. So let's say I have an existing model, let's call it v1 of my model, and that v1 model sort of is giving me good results, and I want to push a v2 model, which is a deep learning model, is like super awesome and it should give me better results in theory. The way I do it is that I just expose 1% of all of my traffic to this new model which I've built, and then I see how it's performing, right? This is also called A/B testing or Canary deployment. And essentially based on how it's performing to this, I'm gonna say that okay, this model is good, let me increase 1% to 5%, then 10%. So that essentially means gradual release cycle. um, Software development also follows that. Oftentimes you might have observed that if there is an application, some people receive an update, some people don't receive an update. That is also A/B testing. They gradually release it. ML modeling, we do the same thing. Multiple models are deployed at the same endpoint using Vertex AI endpoint, or any of those sophisticated solution. You can use the same endpoint URL, which means that you will be using the same URL, but you will have multiple models. You can have two, three, I don't know the upper limit, but you can have multiple models deployed at the same endpoint. And depending on some equation, it will decide whether or not a user should hit the v1 model or the v2 model. So that's why I feel that personally Canary deployment is excellent when you have a new model which you want to deploy and you want to reduce the risk of it failing. So let's say the model is going to fail, I don't know about it, but I only deploy it to 1% of my end users, and I can see that their experience on the app, their retention is reducing. So I can just undeploy them, or I can roll back my changes. So we can move to the next slide. Cool. So now that we discussed these, now let's discuss about model monitoring. Right, like we just discussed, if it's an online deployed model, it's extremely difficult to take care of what is going on in the model. It's not a batch inferencing where you can have all the outputs. So fortunately, we do have Vertex AI does provide model monitoring tools, and I've personally used them quite often. They're like superb. So these tools generally have these two major things which they work on. So there are different types of monitoring which we can do, is the training serving skew detection and the model prediction drift or model drift prediction. So when we talk about the training service queue, it basically means that my training data was, had some distribution. Let's say it had normal distribution, but unfortunately or somehow my serving data or the real world data which I'm getting is a logarithmic distribution. So there is like a huge skew. But if you already have your training data with you, you can sort of use the vertex AI modeling, model monitoring, to figure out that, hey, my data, right, serving data is changing very much as with respect to the training data, and it will send you an email to tell you that, hey, it's a time to retrain your model, right? Or if you it's a part of a pipeline, you can just retrain the whole pipeline, right? And similarly, we have model prediction drift, which simply means that the the data which the model receives, the data distribution is changing over time, right? Let's say, uh, let's say my V1 model was working excellent in the winters, right? I built this model, it's working excellent in the winters, but as we approach to the springtime and the summertime, the model is deteriorating. So how will you detect that the model is deteriorating, right? It's an online model, it's you're just getting 2 or 5 requests per day. How will you know it's going bad? You can use something like a model prediction drift. So it will understand that the results are drifting away from the real results, they're getting poorer and poorer over the course of days or months, and it will sort of intimate you that, hey, it's time to train a new model, or there's something wrong with your data, or something is going on with your model. So these are like exceptionally good tools, and any production environment you would have these set up, right? Because you cannot deploy the model at the mercy of just hoping your fingers crossed the model will work. It doesn't work like that. It will fail very badly if you don't do this in a production setting, right? So these are the methods which work well for both categorical as well as numerical features. This is the only two features which are supported. Cool. So now let's move to the next slide, which is the most probably the one of the most interesting slides. So after knowing all this, right, let's move to MLOps, right? And MLOps, I know it's all the buzz. Everyone is talking about it. I myself included. So what is MLOps, right? It's just a set of standardized processes and capabilities for building, deploying, and operationalizing ML systems and algorithms rapidly and in a reliable fashion. One thing to notice is that we never mention ML models, we mention ML systems, because ML models in itself are useless. Right? They cannot do anything. So it's like, if you have, even if you have the brain of the most intelligent person, but if it's stored in, let's say, some, in a cold jar or somewhere for an experimentation, you really can't help it out, right? You want something else with it as well to make it work. So that's why we call it ML systems and not ML models. So here are the different things, right? Starting from the top, you have ML development. Then you have training operationalization, basically operationalizing the whole training workflow. Continuous training, that can happen when your data changes, or again, like I mentioned in the previous slide, if your model drift changes or training serving skew happens, you can trigger a continuous training. Model deployment, again, deployment should also happen continuous way. Basically, you trained a new model, it should automatically deploy the same model, albeit it should be a little, it should limit the amount of traffic hitting to it. And there's the prediction and serving as well, and continuous monitoring. So all this cyclic approach, right, it forms the basic of an MLOps. So the way to explain MLOps, or the way to think about MLOps, is the way to sort of understand that if this ML model is to be used by my end user, or by my customer, or by my client, whoever, then it cannot be a standalone model, because ML models degrade very fast, because ML models are data dependent, right? So moving to the next slide, it will make it a little more clear. So before answering the question, why does MLOps matter, let's look at the Venn diagram, right? So there is something called as machine learning, which everyone is interested in. I mean, I would think everyone in this call is interested in. Then there's data engineering, because ML and data are tied together. It's like the perfect marriage. And then there's DevOps. So DevOps basically means to ensure that you have CI/CD, you are continuously changing code, and you're pushing the code, and it sort of deploying things on its own, right? That's what DevOps mean. But just the way in DevOps, you can change code or change some parameters, and it auto deploys the code, and it auto deploys the application. The same way you can do it in ML as well. So you change some code in ML, you change some data in ML, or you change some parameters in ML, it should automatically trigger the training, it should automatically trigger the evaluation, automatically trigger the model deployment, model predictions, monitoring, all of those things, right? It should be automated, because nobody is going to sit there and wait for 4 hours for the model training to complete, then go and click on the buttons, run some code, do analysis. Nobody's going to do that, right? All of that should be automated. That's where DevOps comes into play. And the interesting thing to note is that it's not just DevOps plus ML, it's also data engineering, because like I said, your data can also change. And if you know that your data is changing, you should go for an automated approach, right? If you know your data is changing very fast, like I mentioned, seasonal things can happen, right? Let's say now Christmas is coming in next week, right? So your trends are going to change around holidays, right? People take a lot of holidays, people have spent a little more, spend a little more money on gifts and all those things, so your trends will change. So if your trends are changing, your data is changing, that should be integrated with your systems. So why does MLOps matter? So MLOps focuses on the intersection of data science, data engineering with the existing DevOps practices to streamline model delivery across the machine learning development cycle. So if you have a machine learning system, not a model, a system, you want to make sure that end to end, whatever happens, it should be streamlined and automated, right? There should be minimal human intervention, especially in terms of ML, because there's generally a lot of moving parts. There's data, there's DevOps, there's ML, fundamental ML or deep learning happening. So in that case, you want to abstract it away and you want to make it in a very robust sort of a fashion, right? And oftentimes what happens is that when you deal in ML, when you make ML systems, you're running a lot of experiments. So in my humble and personal experience, MLOps matters there as well. It's not only about delivery. It's not only about doing it for a user or doing it for an end customer or doing it for your product. It is also important while you are doing experiments, because if you are running 10 experiments, you can do it manually. You don't need to worry about training, monitoring, and all those things. But if you are running 100 experiments on 10 models, right, that means you have 10,000, sorry, that means you have 1,000 iterations. So at that time, you will not do it manually. You need to have an MLOps pipeline, which is what we're going to cover in the next slide. Cool. So, like we discussed, the ML life cycle. So, what do you mean by ML life cycle? We have these steps, right? It's a very high level steps: data extraction, exploration, preparation, model training, evaluation, validation, serving, and monitoring. So, and on the right side, you have this image, right? This image sort of showcases what all things are available, and this is particular to Google Cloud because we've personally used it. So this sort of showcases at what stage what component you should use, right? For data readiness, there is like services of Vertex AI data sets, data labeling. For feature engineering, you have feature store, or you can use any other VM, Jupyter VM as well, even Vertex experiments. For hyperparameter training, you have Vertex Vizier and AI accelerators. Then you have model serving. Again, like model serving, which is discussed a while back, you can use Vertex AI endpoints. Then tuning and edge, these are additional things which you may be interested in. And then there's model monitoring, again, continuous monitoring, like we discussed. And there's model metadata, which we also discussed for model management, right? Model management becomes especially useful when you have a lot of models in your system, which most AI companies or even AI products have, right? So data extraction, you can use the first section, data exploration, the second subsection, third point as well in the second subsection. Training, evaluation, validation, you can do it with AutoML or you can do it in a custom manner. Serving, again, you can use Vertex AI endpoints, and model monitoring we discussed a while back. But in this diagram, if you observe, there is one very interesting thing, right? All of these subsections are very small, like experiments, prediction, hybrid AI, notebooks, except for one subsection, which is the bottom. It's called pipelines orchestration. So it's a little high level, may not be always required, but when you are doing in end-to-end deep pipeline building, you need to use pipelines. You can use TensorFlow extended pipelines or Kubeflow pipelines or any other sort of pipelines which you may be familiar with, MLflow pipelines. This basically means that some software needs to orchestrate this end to end. So right from step 1 through step 8, no human being is going to sit there and do it manually, right? Think of these 8 steps as something which is continuous, right? Which is going to happen each time. So let's say you are building a new model. right? But you want to run 20 experiments with it. So you will not repeat these 8 steps 20 times manually, right? That doesn't make any sense. So what you will do is that you will create a pipeline. You will invest some time in creating a pipeline, and you will have these 8 components in the pipeline using the relevant whatever, relevant features or relevant tools. And then you will run the pipeline for 8 different experiments. So you will build the pipeline once and use it multiple times. So build one, use multiple times, right? Yeah, if we move to the next slide, we will have like a better picture of what it all means. So if we wrap it all together, we have the ML lifecycle, we have the ML model, how do you build the model, how do you manage the model, and what are the different aspects of it. So the first thing is model development, then data processing, then operationalized training, which basically means whenever your model deviates, your data deviates, your code changes, you need to operationalize the training. It should happen in an automatic manner. Then deployment and serving, then workflow orchestration. Again, workflow orchestration means that all of this should be automated, no human intervention should be needed ideally. Artifact organization, again, serving hundreds of experiments or whatever experiments you're running, you should be able to save it in a particular manner. And then model monitoring, again, because model monitoring is essentially the feedback loop, which will sort of cover the ML deployment, the serving. It will understand how it's working in the real life and give you it will give you feedbacks. It can even give you email alerts, or you can even have certain type of alert setup that if your model is performing worst, if it's dropping the accuracy to less than, let's say, 60%, then just delete this model or roll back this model to a previous model which worked much better, right? So essentially that is wrapping it all together. This is a little high level. These sort of systems and subsystems have a lot of intricacies which are inside them. Nobody expects you to know them on day one, but this is how ML happens in the real world. Model development is just a small piece of the pie, like you saw in the first pick. The real deal is how you make sure that the model lives and survives in the wild, right? So we can move to the next slide, and with that, I conclude the session. So I'd love to take some questions now. I hope it was a useful session, and folks have some questions to ask. Okay. So difference between DevOps and MLOps. I would say that MLOps is like or rather, DevOps is the part which builds for the latter part of MLOps. So in DevOps, you have CI/CD. You use it to build applications and have continuous integration and all those things. Right, all those things. Interestingly, in MLOps as well, you do that. So in MLOps as well, you use DevOps concepts. So if you know DevOps, it is much easier to use MLOps. So essentially, think of MLOps being an extension of DevOps for machine learning. But with DevOps, you don't bother about data, but with MLOps, you have to bother about the data as well. Right? I hope that answered your question. Meanwhile, I'm going to move to the next question. So what is the difference between DevOps and MLOps? We've taken care what tools we can use for MLOps. So for MLOps, like I mentioned, right, MLOps, it's like a huge umbrella. So if you ask what tools you can use for MLOps, it's a little broad sort of a question. What I think you mean is that how do you create these pipelines? How do you orchestrate these pipelines? Because tools, like I mentioned, we discussed a bunch of tools based for monitoring, for deployment, and for uh, post processing, even serving. For MLOps pipelines, you can use tools like Kubeflow pipelines,
Those are really good. If you have TensorFlow native code, you can use TFX, TensorFlow extended. It has a little learning curve to it, but it's exceptionally good if you have like native TensorFlow operations happening, right? TF dataset, if you're using, are you using TF record files, this TFIO operation, all those things, then it works really well. MLflow also supports pipeline, so you can use MLflow as well. It's also open source. um okay. How to decide which model we have to use on given data sets. So basically, you, in order to decide which model to use for which data set, you should have enough understanding of the machine learning problem at hand. The best way to do it is to research, right? So if it's a basically, if it's a structured data sets, then you would go with a different set of modeling approaches, or what is the problem statement at hand, right? If you want to do clustering or you want to do unsupervised learning, you'll use those techniques, or you'll use if you have labeled data, then you'll go for either so if you have a labeled data, then you will go for structured training approaches, or you can even go for reinforcement learning and all those things, right? So it all depends on what type of data you have, um, and what problem you're solving, right? You can use the same data set and remove the labels and go for clustering as well. um, which tools to use to hackathons and quickly deploy a model. So I'm not sure about hackathons, but if you want to quickly deploy, you can go with fast api. I've heard it's really good. Generally, I have in the past used it depends on the model as well, but I've in the past also used Flask based APIs. If you are good with those are also helpful. Little learning curve. If you are using TensorFlow native models, you can go for TF serving. Little complex, but you can definitely use that as well. Mm, MLflow, how would you recommend? I would recommend it. MLflow is a good open source alternative. It has good artifact tracking as well, and experiment tracking as well. So yeah, I would recommend MLflow. I've personally not used it in the industry, but I know it is used quite a lot in a lot of in a lot of organizations. Mm, in training servings detection tool data. It is monitored in the real time, but it is not recommended to monitor each instance, right? Because it's an online serving, so the expectation is that you want to monitor 1 out of 5 requests, or you want to monitor, let's say, 20 times in a day or something like that, right? Because otherwise it'll become too expensive. So you would want to it's a trade-off, right? How much requests you have basis how much you want to spend for that. It depends on that. You can set up your local instances to do that as well, but if you do it for each request, it's going to cause a lot of latency, and it's also going to be expensive, right? You're running, it uses, I think yeah, I don't exactly remember the algorithms, but it uses some good statistical algorithms to figure that out. Some resources on MLOps. I would recommend to go through some Coursera courses. I mean, I'm not sure if there are good ones, but if you have Google Cloud credits, you can start practicing them on your own. But I think Pluralsight and Coursera have really good courses on MLOps, especially MLOps on GCP. I would say that stick to one platform, one cloud provider, and learn all the concepts. Concepts are transferable. So if you learned it for, let's say, GCP, you can use similar concepts in AWS or Azure as well. Um, it's just that if you are comfortable in one cloud, you understand the fundamentals, then you'll be more comfortable moving to other things as well. So main challenges in operationalizing ML models. So almost everything which we discussed is it becomes a challenge, right? um, your inference latency is the one which is almost always bothered folks. So depending on the use case, you might want to quantize your model so that it doesn't take that much time that as it takes, right? So that its operational latency becomes less. Other thing is that operationalizing ML models, ML ops is generally really complex, um, especially if you have stakeholders who approve or disapprove models, because the end outcome of an ML ops system or an operationalizing system is to push a model to production. in general, when somebody has to take a call, right, what should go to production or what shouldn't go to production, that person is generally in a lot of pressure, as you can imagine. So they need a lot of data to, give the green signal to say, hey, put this model into production. So convincing them, having those right insights, having those right data pop up, is something which I would say is a challenge. It's not a technical challenge as much as it is an operational challenge, but yeah, technically as well, it's generally gets a little complex because there is like a lot of things happening in ML model, and there's a lot of points of failure in this process, right? So you need to make sure that all of these points are plugged. Okay, I'm just trying to get some resources for MLOps. I think there is one. Let me just share it with you. So this is like a good blog, which I think I also had referred a while back. Um, this is like a really good blog, which I sort of had referred a while back, which worked out quite well. Um, just sharing it. It basically takes a dummy example of an AutoML model and showcases how a pipeline works. So it is using Kubeflow pipelines in the backend, and it sort of covers each aspect, like how data processing happens, how model data set creation happens, how pre-processing happens, how model training happens, and how deployment happens. So it's a really really good blog to read to get the overall idea of how MLOps works. Again, like I mentioned, MLOps is vast, and in general it is cloud agnostic, but if you understand one, then you can sort of use the same sort of knowledge across different clouds. So this is the blog, right? You can just share it with folks. Okay, it's an interesting question. Do high-end models hybrid inferencing? How do they handle so much load? It depends. So the way it works is that Dheeraj, is that oftentimes what happens is that when you talk about any high-end models, right, which have a lot of data, it does use some sort of pre-computations. So it sort of has pre-computed outcomes of a lot of of a lot of iterations. It has some pre-computed outcomes, and it sort of uses that. They use a parameter server approach, um, and they also sort of cache all this information, right? So if some features which you are gonna query are already known before you even query it, or you hit the model, right, those are directly stored in memory, and they are run, so they're much 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 faster. So oftentimes, yes, they do use hybrid approach, or basically what you're calling a hybrid inferencing is not technically hybrid inferencing. It's called um, a feature store based approach, where some of your features are pre-computed and already stored in like a in-memory database, like a Redis database. or they're saved in, basically they are already in memory and they can just click on it, you can hit the model, it already knows the features. You're using an open source AutoML framework of Flamel. Can I operationalize it to browsing? Okay, so I'm not sure what a Flamel is. So if you are able to get the model serialized output, you can use it. um, I am not sure because I've never used Flamel. If you're able to get a serialized model output, like you can get the model files out, then you can operationalize it in the same way, right? The way you do it. You may have to write a lot more boilerplate code, but it's still possible. Yeah, it's pretty similar to caching in other fields, yes, but unfortunately feature processing is very expensive because it's uh, the number of permutations and combinations are humongous in machine learning, right? So there's a lot of users, there's a lot of content, or let's call it items, right? So the combinations are humongous, so it becomes really expensive. So generally you avoid doing that. So there are certain ways to mitigate that. You can pre-compute the values and store and estimates of those things, but it also depends on what type of machine learning problem you're solving. If you are trying to solve a problem which is like a recommendation based on vector search, there are algorithms which sort of do search space, which use the search space, and instead of searching the whole space, they know which space to search. So it's like a inherent clustering algorithm. So if you're interested, it's called scan, SCANN algorithm. So depending on your ML problem, there are ways to optimize it without touching the model. You can optimize stuff without touching the model. Um, Hybrid inferencing, personally, if you ask me, I have not heard of it. It may exist. Maybe we're both referring to the same thing, but I am not aware of the terminology because I've never heard of hybrid inferencing. Like I mentioned, it's either online or it's sort of batch processing, or the other way is to have these kind of, if you're doing online processing, like online inferencing, oftentimes you will use a feature store, you will use an in-memory database to sort of have pre-computed feature values, right? um, so things like if you are clicking on an ad, right, based on your recommendations, it will generate more ads. It already knows your geographic location, right, your watch history and all those things. So those are not delivered to the model in real time. Instead, it sort of stores that information already and goes on appending it as you're interacting. So essentially, though it is online, but it already has a little bit of your information stored in its feature store. But those are expensive. They use parameter server approaches. So I'm not aware. I'm definitely not aware of what does Twitter use. So All right. Thank you for your questions, folks. It was a great pleasure delivering this session, and hopefully, it was as useful for you as I think it was. And yeah, I mean, if you have any more questions, you can post it now, because otherwise we're mostly winding it up. But yeah, I mean, thanks a lot for joining, and hopefully you didn't get bored, or it did not sort of wasn't a bouncer session. You got some reliable, or maybe rather easy to absorb information from me. And yeah, thanks for joining.
Yeah, it was really and truly like insightful session. Like we got to learn a lot of stuff, like whether from knowing about the various terminologies, whether it's artifact tracking or data lineage, or like not only the features but also like when we are going to use, when we will be needing it while deploying the stuff, and also about batch inferencing, the pros cons, and also the application in the real world, and like and also about the model monitoring methods and what procedure we should follow with the documents and also the resources to learn from. So it was really an insightful session. Thanks a lot for the session. Yeah,
It was a pleasure.
I hope it's
Yes.
same for everyone who is attending. Yeah. Thank you everyone for joining.
Yeah,
Right.
exactly. I think yeah, it was informative in every aspect. Like why an ML engineer, if you're aspiring to be an ML engineer, why you should be acquainted with ML ops. Like it can help you save a lot of time for an end-to-end model integration. Yes, you might as well check out the resources we have pinned it in our comments. You can go and read that blog. Thank you, Gopala sir.
Yeah, thank
All
you.
right. Thank you, everyone, and have a good night. Bye bye.
Bye.
Yeah, bye.